Okay, one last piece of instructional advice that might be helpful here is that, we're working with this situation where y equals y sub 0 e to the kt. If k is a positive value, then we're talking about a situation where growth is happening. And if k is a negative value, like in the one that we're about to work, then it's a decay issue. The amount is decreasing over time. Okay, we're talking about radioactive decay in this example. This has to do with radioactive isotopes that all have half-lives. The half-life is the amount of time it takes for the initial amount to become only half of what it originally was. And each isotope has a different half-life. Some have half-lives of only a few minutes. Some have half-lives like the ones you see here of several thousand years. So we're working with a scenario here on the first line of this table where we want to find this radium isotope's amount after 10,000 years. If its initial quantity is 3 grams and its half-life is 1620. Well, I can label one of these columns right away. I know that the initial amount is y sub 0 because that's y if t is 0. And we saw in the last video that if t was 0, this whole term just became 1, and my y value is y sub 0. So here's y sub 0. I think I can use this column to find k, because if y equals 3 e to the kt, I know what y sub 0 is now. I know the amount of time it would take for half of that amount to show up. So I know that after 1,620 years, I know that my amount should be half of 3, 1.5. That's what the half-life is. So I think I could solve this equation for k and find that value. If I divide both sides by 3, I would get 1.5 over 3 equals e to the 1620 times k. Multiplication can happen in any order. I could do ln of both sides. So ln of 1.5 over 3 would be ln of e to the 1620k. That's just 1620k. So I know then that k is going to be ln of 1.5 divided by 3 all over 1,620, which is a value I can get from the calculator. So ln of 1.5 divided by 3, then that divided by 1620 gives me about this value of negative 4.27 times 10 to the negative 4th. Okay, that's scientific notation. So that would be negative 0.000427. There's my value of k. And now, if I know k, and I want to find the amount after 10,000 years, or in other words, when t equals 10,000, I should be able to. I can use y equals 3 is the initial amount, e, I've got my value for k, 0.000427. It's negative, of course, and that's good. It's worth pointing out that it was good that we got a negative k because this is a decay problem. Times the value of 10,000 years. And there's another value I should be able to crunch from the calculator. Okay. So if I've got 3e to the negative 0.000427 times 10,000 comes out to about lost it, 0.0419. And that would be, that's an amount, that's grams. Yeah. So there we go. Now we want to work in the second line of this table where it says we're working with carbon-14. That's the isotope they use for a lot of when you hear about carbon dating to determine an approximation for the age of artifacts and fossils and things like that. That's the isotope that they're referring to. It has a half-life of 5,730 years. And here we know the amount after 10,000 years. They want the initial quantity. So this is a little bit of a different beast here. I know y equals y sub 0 e to the kt still. And I do know one pair of this. I know that after 10,000 years, so when t is 10,000, I'll have an amount of 5.4. I don't know y sub 0. I've got e. I don't know k either. But I know that I've got a value for t that works for this value for y. You know, I've got two things I don't know. I don't know y sub 0 and I don't know k. So it would make sense that algebraically, if there are two things I don't know, I need to write a second equation. And I think the other one's going to come from this idea about the half-life. I don't know what y sub 0 is. But I know that if I let t be 5,730, I don't know what y sub 0 is, but I know that my value after that many years is going to be half of that. So I could call that 1/2 y sub 0. If you need to, pause the video for a second and see if that makes sense. Think through that. And the good news here is that since y sub 0 isn't 0, I can divide those out. And I can just solve this equation for k. I could take ln of both sides. Ln of 1/2 is the same as ln of e to the 5,730 times k. That's just 5730k. And if I don't want to solve that equation for k, well, I could just divide both sides by 5730. So I've got ln of 1/2 divided by 5730, and we're back to the calculator. Ln of 1/2 divided by 5730 gives me a value of k for negative 1.21 times 10 to the negative 4th, which is negative 0.000121. And now I can find y sub 0. So I've got a value for k. And now I might use the scenario here. In fact, I suppose what I really should do, my apologies, is just take this other equation we were working with and plug in the value I know for k. So let's say 5.4 is y sub 0 e to the k was negative 0.000121 times 10,000. And you know, this may look like a complicated equation, but essentially you just got the thing you want, y0, times some number. This is a weird number, e to the product of two numbers, but that's just a number. So I could divide both sides by that. I could say y sub 0 is 5.4 divided by that value, e to the negative 0.000121. Do some canceling here, I suppose, times 10,000. But since we're looking for an approximation, let's just crunch it. 5.4 divided by e to the negative 0.000121 times 10,000 Comes out about 18.109. And that was an initial amount. So that in this case would be grams. So there you have it. You're going to try a couple of examples that involve this radioactive decay concept as well. You're going to also work a couple of examples that involve continuously compounded interest. But this same scenario applies. I don't want to run through in the video exactly this, but essentially you've got your annual rate. I would remind you that this is a value that, since it's a percentage, you should use as a decimal. So your R in this case would be 0.055. Okay. And actually, so you're going to work with, here's your initial amount, here's Y0. In fact, I think we'll go ahead and run through the first one here. So if Y is Y sub 0, e to the kt, you can say that your initial investment is $20,000. You got E. You want to find the time to double. You want to know what time it's going to take for you to get to $40,000. And it turns out that your rate, your constant here, your constant of proportionality is that rate. So you could actually solve this value for, you could solve this equation for t. You could divide both sides by 20,000, which will just give you 2 equals e to the 0.055 t. And then you could do ln of both sides. Ln of the right side would just be 0.055 t. And then you know that t is ln of 2 divided by 0.055 rather. Which gives you a value of about 12.603. And that's a time, so that's in years. And you can work the rest of this table similarly. You know here that t is 10. Okay. So that'll be a task you've got to work on here today. The good news here, though, is that in each of these scenarios, you don't need to solve the differential equation we solved in the last video. It's been done for you. Thanks for watching, and good luck.